Hi, everyone. Thanks for coming. Um, this is Marks of Intelligence. This is part of the Idaho Library Tech Talk series at a slightly different time for a slightly different reason because I'm also going to selfishly be promoting, I think, what is a really, really cool project that I'm looking to get some help with. So the plan for today is to give you a kind of history of some AI benchmarks. I classify them roughly into those that are like man versus machine, then man versus data sets, and I'm going to focus a little bit on vision and natural language understanding. And then I will turn to the age of massive scale models that we've seen in the last 5 to 10 years, some of the challenges and limitations that come with benchmarking them, some important distinctions that have emerged in those challenges, and then I'm going to present on some of the frontier benchmarks of measuring intelligence and some of their emergent capabilities. So I would be remiss not to go back all the way to at least Alan Turing, who in a very famous paper introduced what we now call the Turing test, or what he called the imitation game. This is the 1950s a paper that I highly recommend reading called Computing and Machine Intelligence. And what his innovation was to take a game that looks like this, where you have 3 people. You have person A, who's a man. The man's goal is to be deceptive, to try to convince C, the interrogator, that they're a woman, not a man. And then there's B, a woman, whose goal is to actually get the interrogator to correctly identify them. The key thing is that they can only interact through these teleprinters that they have, so only through text. And the interrogator can ask any kinds of questions that they want, always through this sort of texting format. And if the interrogator only gets a 50% chance of getting it right, that's like flipping a coin, then the man here has done the job of deceiving the interrogator that they were a woman as opposed to a man. So it's a sort of social, psychological experiment. And what Turing thought was, wait a minute, I could turn a game like this into a kind of what he calls an imitation game, where now we replace, instead of a man, we replace that with a machine, whose goal is to deceive the interrogator that they're a human. And we replace B with not just a woman or a man, but any human. And their goal is, again, to be correctly identified as a human. And again, it's just teleprinters and teleprompters that you interact with. So this has become quite famous, known as the Turing test. There's been various versions of it that have sort of removed different kinds of identifying marks and tried to move more towards communication and intelligence. It's been a long-standing kind of test. And there's a couple things that I think immediately we need to remind ourselves of, some lessons. So first, Turing's goal was to take what, especially at that time, was a very sort of deeply philosophical question and try to replace that question that he thought, you're not really going to make any progress on this. It's just too hard to try to figure out what counts as thinking and what exactly gets to count as a machine. So he replaces this question with this thought experiment, this imitation game. So one way to understand this sort of advancement is to taking a kind of philosophical question and operationalizing it in a certain way so that we can talk about intelligence in some kind of empirical format, in some kind of empirical discussion. Some additional things to keep in mind about that is that passing the test is not a necessary condition. So you can be intelligent, you can be a thinking thing, and still fail at that conversation. It's not meant to be a necessary condition. Arguably, it's not supposed to be a sufficient condition either. Right? And the reason for it being neither a necessary nor sufficient condition for being intelligent is this distinction between what Noam Chomsky made later on between performance versus competence. Your ability to perform some kind of behavior, whether it's intelligent behavior or some kind of conversation, depends on you having some competence to do that, but also a bunch of other conditions in place. If I put a piece of tape over your mouth and you can no longer speak, that doesn't mean you don't have the competence to speak. It means you are not able to perform because something's impeding you from doing that. So we have to keep this in mind. Just because you're seeing some evidence of something having certain kind of behavior, so you're seeing a certain kind of performance, doesn't automatically mean that it has the competence for doing that. And that goes in both directions. Either a lack of performance doesn't mean right away no competence, and having the performance doesn't automatically mean you have the competence either. And the other key thing is humans are judges. It's a human interrogator there. And to that end, there's a bunch of other kinds of benchmarks that emerged, largely in the form of some kinds of games. Conversations are unbounded, right? So initially when we were trying to build machines that could actually pass something like the Turing test, like where do we even begin? And there are some important and fun programs that end up working. I won't talk about them here, but one of them is known as ELIZA, which pretended to be a therapist by just taking anything you said and turning it into a question and then sending it back to you. That was sort of a programming trick that was done. But in general, like conversations are just unbounded. You don't quite know where it's going to go. And that made them really intractable as a kind of starting point. So instead, there was a push towards games like checkers and chess. Why? Well, because there's a very clear definition of success. You won or you lost. And in addition, there's some finite sets of rules that you need to follow, and there's discrete states, discrete board states in chess and checkers. Probably one of the most famous sort of projects related in the checkers world is known as the Chinook project, appropriately named because this was at the University of Alberta. Started in 1989. Sought the right to compete in the Human World Championship for checkers. Understandably, there was some hesitancy towards that, and so there was a then separate Man versus Machine World Championship that took place in 1992. And the Chinook project, this program that they developed to try to beat the best human players at checkers. Oh, did I just step on the cord? Sorry about that. Lost to Marion Tinsley, but then second.
The screen share stuff.
Oh, sorry about that. I think what happened is I stepped on the cord funny.
Thank you.
You bet. Okay, so in 1992, there was the man versus machine competition. It lost, but then in 1994, the Chinook program won, beating Tinsley, though it is a little bit interesting that Tinsley actually withdrew due to illness, but there were 6 draw games. And so this is interesting. There were 6 draw games, not a winner. And so that led to some suspicions, and by 2007, checkers has been solved. And what we mean by that is it was weakly solved. It means that the best play from both the sides, both players, if they play perfectly, you will just inevitably lead to a draw game. So in that sense, checkers has been solved in the same way as like Connect 4 has been solved, right? Or tic-tac-toe has been solved, right? If both sides play perfectly, you end up getting to a draw. Checkers has been solved. Chess, not so much. Chess is far more open-ended and requires a lot more board states to keep track of and a lot more moves to keep track of. This is probably more famous. This was IBM's Deep Blue project. In 1996, Deep Blue ended up winning its first match against Garry Kasparov, who was the sort of world champion and leader at the time. Kasparov sort of changed strategy after realizing, okay, wait a minute, I need to actually like treat this thing in a slightly different way. And Deep Blue ended up losing to Kasparov 2-4. And then in May 1997, there was a rematch in Deeper Blue because they did actually do some changes to it to play different strategies, gave it more data, and gave it much more computing power. Ended up winning 3.5 to 2.5. So some important things to keep in mind when it comes to these gaming kind of benchmarks. Checkers and chess, they're discrete. They're closed formal systems, right? You can't sort of do a certain move that is an illegal move, right? That will just not get counted as a move, right? In these situations. They create what we call like game trees. So you can imagine that your starting node of the root of the tree is sort of the starting position of the game. And then all the different possible moves are your first set of branches. And then after that are all the next possible moves. And there's going to be a lot of those branches. But what it does is it sort of provides a very defined kind of discrete space that makes a search tractable. You know what things you need to be checking for. What you need primarily is enough computing power to search all of those branches because they grow very, very, very quickly. The other thing to note is that these sort of discrete formal games, they are actually far more specialized and they're less representative of general intelligence. There's what's known as the Merivok paradox that was written about in 1988, and Minsky and Brody and some other famous AI researchers sort of had adapted in various ways. But he said, it is comparatively easy to make computers exhibit adult-level performance on intelligence tests or playing checkers, and difficult or impossible to give them the skills of a one-year-old when it comes to perception and mobility. And my favorite examples of this is to make a robot walk through a doorway. Turns out to be so simple for a human, but turns out to be extremely difficult in robotics. And I think even more famously now is just load the dishwasher. You can get your toddler more or less to do it at this point. It's basically hopeless still for any robot to be able to do this. Okay, so that draws the sort of like story for like man versus machine. Now I'm going to turn to a sort of like man versus data set type of benchmarking. And here the thing to note is instead of using a human, say, as the primary sort of benchmark, you end up having a data set that you divide into two. You have what we call the training set and the test set. The training set are all the examples that we think are fair game. The machine gets to learn, gets to see these in advance, tends to be typically very, very large. The test set is where the real benchmark is. The test set are the examples that you'll then evaluate a machine on. And ideally, those examples in the test set weren't in the training set. They're meant to be new, right? You're trying to figure out whether the machine didn't just memorize a bunch of things from the training set, but it's sort of learning to generalize. So the examples in the test set should be unseen, at least relative to the training set. And sometimes we'll also develop what's called a human baseline. So we'll get humans to answer questions from the test set as well. And we might realize, like, you know what? The test set is hard enough that no human gets it perfect. Humans maybe get it 80% correct. So sometimes when you hear these things like, oh, the machines can surpass human benchmarks, you're like, how is that possible? It's because we took a baseline in the test set, and the machines are actually doing even better than the average human benchmark in the test set. Okay, so there's this sort of nice empirical turn now. And what I want to do is give you a couple examples of these. The first one, and I can classify these, as I mentioned, into the vision and the natural language understanding part. So in the case of vision, in the late 1980s, the Census Bureau wanted to automate handwritten census forms. That would be very, very convenient. And so they developed these databases. There's a variety of them, but most of them were based on what are called these handwritten sample forms. And here's an example over here. On the right, so there's this handwriting sample form where you need to put in things like dates and certain kinds of numbers that you need to write. So they have the typed version of it, and then you have to handwrite what that is. And then they also say, please print the following text below. We, the people of the United States, in order, and then so on, right? So what you have is this corresponding digital text and the handwritten form of it. And now you have this data set. This is the NIST data set that you could then use to train vision models. Right? Try to get your models to look at human written text and try to transcribe that into the sort of digital text. Now, the problem that was recognized was that most of the data set examples that were in the training data set was from the American Census Bureau employees, while those in the test set were actually from high school students. So that's a bit too much of a leap, right? There could be significant differences in the handwriting. That's not really a fair comparison to make that jump. So MNIST, I'm not sure, maybe Luke knows what's the shorthand, but MNIST, or the Modified National Institute of Standards and Technology Database, was a version of this. This is actually developed by Jan LeCun, Karina Cortez, and Christopher Burgess. Jan LeCun is now the director of research at Meta, I believe. They basically remixed these data sets, but also in an important way, they standardized all the examples so that you would have a 28 by 28 pixel grid, and there would be a kind of grayscale to avoid certain kinds of distorting artifacts. And in the original paper, they showed that they could get a support vector machine, it's a kind of a machine learning technique, to achieve an error rate of 0.8%, super low. And I think they've recognized that there were 4 mislabeled cases out of the full, I think, 7,000 examples. 60,000 in the training set and 10,000 in the test set. Another big advancement in the vision world is ImageNet. The goal here was to take this noun hierarchy of words called WordNet, which consists of 155,000 words that are organized into what are called synsets. These have to do with like dictionaries or thesaurus types of relations. So you end up getting what's called these like word sense pairs. What they want to do is take that big data set and have images that correspond with it. The result is 14 million hand annotated images across wait, that can't be, that's got to be more than 201 categories. Bert was sick while he was developing this talk over the weekend. In 2010, the main challenge with ImageNet was launched. I think this was the very first challenge. And this is to build models that would classify these images into these distinct object categories, 1,000 distinct object categories. It took only 2 years for this to be solved, or to develop exceptionally low error rate, 15.3%, known as AlexNet. And this is based on what are called convolutional neural networks, which are a particular kind of architecture in the neural network design. That was a big leap. That was 10 percentage points better than the second place. Okay, let me turn to some examples from natural language understanding. I'm going to jump ahead a little bit. There's lots of incremental sort of progress that was made here, but what I think is interesting is in 2018, a data set known as GLUE, which stands for General Language Understanding and Evaluation. It took 9 other existing natural language tasks and combined them into one. Some examples include COLA. COLA was used for trying to judge whether a sentence is actually grammatical or not, right, or whether a sequence of words is grammatical. There was a sentiment tree bank. There was a paraphrase corpus, and then there's a semantic textual similarity. And there's also, from my perspective, as in philosophy and logic, an entailment corpus that looked at whether a machine could determine the logical relationship between a premise and a hypothesis. That same year, Bert, no, I was not biased to pick this out. This is an accident. But Bert stands for a bidirectional encoder representation from transformers. Transformers were the big advancements in 2017 that have led to the large language models that we know of today. The key sort of move here about Bert was, instead of processing text from a just sort of like left to right direction or doing some kind of like shallow concatenation, Bert used what's called like a masked language model. So you would see a full sentence, and you would mask one of the words, and it would have to predict what that word would be. So it's bidirectional in the sense like it's not always just trying to predict the next word going forward. It can use both directions to try to predict what that masked word was. It scored 80% on GLUE. The rate, as you're about to find out, changes really quick. Of course, you now need to have a new one called SuperGLUE. What do? You take a hardest task from GLUE, and then you add a couple more, and here's one of my favorites. There's this Winograd schema design. I say this is my favorite because in graduate school, this is what got me interested in computational linguistics. Here's an example. The city councilman refused demonstrators a permit because they feared violence. If you replace the schema with feared, what does they refer back to? The city councilman refused the demonstrators' permit because they feared violence. Is they, the councilman, or they, the demonstrators? The councilman. Can now replace instead of feared, say advocated. The city councilman refused the demonstrators a permit because they advocated violence. They now refers to the demonstrators. Humans do this seamlessly. So this is known as a NAFR resolution. When we have pronouns like they or other kinds of demonstratives, we know what they refer back to. And here, the key is just in the semantics, what these words mean. Everything else is structurally exactly the same. This turned out to be a really difficult sort of data set to sort of beat, to solve. And then Google's T5 got 88.9% on the SuperGLUE data set, I think that very year as well, compared to the 89.8% human baseline, right? So this means, again, the test set, the average human might not get all of them correct, right? The baseline would have been 89.9%. So what we find ourselves in is something like a benchmarking treadmill. You have some kind of challenging benchmark that someone creates. The research community focuses on that benchmark. You get some rapid progress. You then get what's called saturation, which we'll talk about in a second. And then you need to make some new benchmarks to create what's called like more headroom. We're seeing this again and again. In 2020, we have the massive multitask language understanding data set. It's 15,000 multiple choice questions across 57 diverse subjects. A average, or the human benchmark, is 89%, and that was in 2020. Here's a plot that I got from the Meta School website. This is January 20 when this was introduced. This is basically like chance, right? 25% chance if it's multiple choice tests. And we see that by 23, GPT-4 has gotten to that same benchmark level. Of course, just like you went from glue to superglue, MMLU had the pro version, which let's add more reasoning and let's make the answer choices broader. So now we go from 4 answer choices to 10 answer choices. And that was introduced in June 2024, and already you can see as the releases come out, Gemini 2.5 Pro is getting 87 something odd % on this thing. Okay, saturation happens when a machine or a model can effectively achieve the human level, does so quite quickly, and when lots of models can do that, it's hard to know what the differences are between them in terms of their capabilities. So headroom refers to this sort of top region. It's good if you can get models to only have like a 50%, say, score on some kind of benchmark, because then there's the differences between them. One that gets 40% and one that gets 50% is much more meaningful. But as they get closer to reaching the human level version, between say 88.9 and 90.1, that difference is not very meaningful. What we seem to be running into is our ability or the sort of progress on developing models that are sort of passing or reaching the saturation point of benchmarks at a rate that is much faster than us creating good benchmarks so to determine the differences between them. Now, in some ways, this is not too surprising. If you've known about Goodhart's law in the context of monetary policy, Goodhart famously said, when a measure becomes a target, it ceases to be a good measure. And if you're like, hey, Bert, we follow lots of metrics at the university. Yup, you should always be thinking about Goodhart's law. As soon as there's a benchmark or some kind of metric and everybody starts going after that, that metric is typically not a very good metric anymore. It was at once a proxy for something, but now we're just chasing those numbers, not what those numbers were supposed to mean. It applies also in the case of AI benchmarking. Training to the test or data contamination, what I want to sort of draw attention to is if you have a ton of data to train a model on, it makes it a lot harder that what's in your test set is truly unseen compared to what was in that training set, right? If you have basically the internet and you have some portion of that in the training set, it makes it really hard to make sure that the test is unseen beforehand. And there's some helpful distinctions that I think have emerged in the debates about benchmark saturation and the benchmarking treadmill. One of them is the difference between knowledge and intelligence. The LLMs that we now have more knowledge than any human. They've read more text than you could possibly read in your lifetime. I think the estimate is like it would take you 500,000 years if you were reading for a full-time job every single day. You can't possibly do that. So they're super knowers. But don't confuse knowing a lot with intelligence. I'll say more about what exactly intelligence can mean otherwise. Another really interesting distinction that's come up in these kinds of debates is between next token prediction. So large language models, what they primarily do is given a huge amount of text that you might have provided them, like some context, like suppose I am a doctor and suppose I had a cold over the weekend and suppose I wanted to know what my infectious period was and suppose blah, 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 blah. And it gets all that text like, oh, here's what I would predict would be said next, right? That's next token prediction. That's different than what you might call representations or mental world models. So if we think about how a computer plays Go or chess or checkers, next token prediction would be like you can describe a chessboard with a sequence of labels and pieces, right? You can say king, h6, queen, and so on, right? You can also have a kind of mental or visual representation of where different pieces are on the board. And there's a question about whether these big models actually develop some kind of like representation, some internal representations of something like a board state, or whether they just have this like rough but still quite accurate approximation that is just predicting next tokens based on the sequences of text that they have beforehand. Another, I think, important distinction is when are we shifting a goalpost and when are we actually just like updating our own sort of standards? And what I mean by that is I know that there's a bunch of criticism out there that like, oh, okay, these models, like all we're doing is shifting the goalposts all the time, right? As if this is a criticism against this kind of enterprise. I think instead we should remind ourselves like as a scientific kind of endeavor, what we're doing is actually getting a better handle on what intelligence means in the first place. We develop a benchmark because we think, oh, intelligence probably involves something like this. Models don't seem to be doing this very well. We make some progress on that, the models do better. And then, no, we never really want to say the models were intelligent now, right? It's not meant to be a sufficient condition or necessary condition, just like what I was trying to point out with the Turing test earlier on. Instead, I think what we're doing is making improvements on our own understanding of what exactly is involved in intelligence. So taking these lessons together, there's some frontier benchmarks that I think illustrate that there's actually still a lot of headroom that we can still explore. We just have to be a little bit craftier in how we do that. And this is where I'm going to introduce one of my favorite benchmarks, known as ARC. So the main idea is to start with an idea of what intelligence is by connecting it to novelty. And in addition, trying to connect it with the ability to do a lot more with less, so with much, much less data. So you think of intelligence as a kind of efficient skill acquisition. So this is in contrast to the temptation that we're seeing in a lot of other benchmark approaches, where people are like, okay, let's just make super glue or super glue, right? Or we're going from the MMLU Pro to MMLU Super Pro. Or there's also a benchmark out there called Humanity's Last Exam, where forget it if you only have a PhD. You have to be like at the frontier of research to do this, right? There's a different strategy here that Francois Chalet and myself suggest, which is like, no, this is misguided. What we really want to do is come up with some puzzles that still turn out to be easy for humans, but are hard for AI. That is going to be much more informative about the gap between what we think of as intelligence in the human way and whatever we might want to think about in terms of machine intelligence. And so Francois Chalet has developed what's known as the Abstraction and Reasoning Corpus, and I'm going to show you what that looks like here. So you're going to be presented with, instead of like thousands and thousands of training examples, you'll be presented with anywhere from 2 to 5. Here I'm going to give you 2. Your first example has some kind of input grid and an output grid. Your job is to see, can you identify there's some kind of implicit rule or some pattern that explains this change between the input and the output. And here's a second example. Here was your input, and here's your output. And now you're given the test. This is your input, right? Doesn't correspond to any of the other ones we've seen before. And you need to guess what the output is. Any guesses on what the output should look like? Yeah, Wayne. Yeah. Using a dark blue pixel, fill in the missing corner of squares. Turns out, large language models, a lot of other AI models, are terrible at these puzzles. ARC1, so this is the version through last year, lasted 5 years before any models started actually doing any meaningful progress on this, like single-digit percentage-wise. Meanwhile, the LSAT was beaten, the GRE was beaten, all these other standardized tests that we typically use. You're just like, why should I bother going to law school anymore, right? And yet with these simple puzzles, which not like high school students and even less than high school students can solve these, they were doing really, really poorly until last year. And last year was when we finally started seeing some significant progress. You can see here Sonnet 4.5, the thinking version, ended up getting 60-something odd percent. The human benchmark is supposedly 100% on these. So on the y-axis here, you have an accuracy score. The other thing that ARC pays attention to is like, how much does it cost to solve that puzzle? This is a rough proxy for efficiency. So on the x-axis, you have what the cost is per task. And so there is a grand prize of, I think, $500,000 if you can get a model that will actually be in this zone. So you want it to be better than 88% accuracy, and it should only cost about 10 cents a task. That's ARC1. They developed a new version because what they realized was that some of the models were sort of picking up on some kinds of like patterns that they did have across these different kinds of tasks. There's about 800 of them. So they created a second version called ARC2, and that could reset the playing field. We are now back down to single-digit progress. This is ChatGPT 5 medium, making it around 7%. This is Claude Sonnet 4.5. This is Grok over here. Grok's making it at about 17%, and they're doing it at about like, I think it's like $4 a task or something like that. This is like, I just pulled this, I think yesterday or something like that. There is a person named Jeremy Berman who developed a model now. I think he's about $30 per task, and he's getting about 28%. And these have been verified so that every puzzle has been solved by 2 humans. That's awesome. Tells you a lot about like maybe we're overthinking some of the benchmarks. And I thought, yeah, we are probably overthinking some of these benchmarks. And ARC has become this awesome preeminent benchmark in the AI industry. Like it is now the sort of primary focus of a lot of companies and labs. And yet, when I play with these, what I notice is they tend to have a kind of stem-like tendency. They're like getting you to think in terms of like Lego blocks and moving things around and counting and repeating certain kinds of patterns according to certain kinds of rules or clues that they give you. But humans, we solve problems in lots of other ways, or in lots of additional ways. We make use of narratives, we make use of agent perspectives, we think about goals and desires and what people intend to do, what actions they might perform, certain kinds of emotions, and so on. We also use metaphors and analogies a lot. So the thought was, wait a minute, there's actually a kind of need here to advance another kind of interdisciplinary AI literacy using metaphors. And this is one of my favorite quotes in the area of computational linguistics about metaphors. Each metaphor is a concise but highly productive way of saying that communicates a productive way of seeing. Let me illustrate. Here's a puzzle that we're calling a MARC puzzle. MARC stands for a metaphor abstraction and reasoning corpus example. Here's your input and your output. Give you another example. Here's your input, and here's your output. And one more, third example. Here's your input, your output. Now's your test. It's your input. What do you need to draw for the output? Now, I'm not giving you the bit of text that goes with it. And without that bit of text, without that sort of piece of text that you can use figuratively, this puzzle's hard, right? You might notice like, oh, there's this gray object that seems to move, and there's these like 3 different like pixels, but I don't understand like why it's moving like to some pixels and not others. Maybe it's just random, but it's not supposed to be random. There's supposed to be a uniquely correct answer to this. Like what gives? Here's your clue. The cat wants to play with a toy it cannot see. Cat wants to play with a toy it cannot see. Any guesses? You did this one yesterday? Anybody who has not seen this one or seen this one for the first time is like, oh, I think I know what's going to happen. Yeah, Wayne. Yeah. Where are the cats? Where are the toys? Where are the things that cannot be seen? There is nothing in ImageNet that will tell it, ooh, you should think of this as a cat. The metaphor, we have this amazing capacity to think in these metaphorical ways, to apply some text that might have some literal meaning and apply it figuratively to solve a puzzle. That's MARC. That was created by an undergraduate student last year in one of my AI ethics classes. And there's a whole bunch of examples that I'm showing you here. This one is called Splitting Hairs. This one's Follow the Yellow Brick Road. This one's called Survival of the Happiest. This one is about the trolley problem, moral dilemmas. This one, I had no idea what to do until I was a student in ecology that talked about mating seasons of elk. And I was like, oh, you got to be kidding. And then all of a sudden I was able to figure it out. There's all sorts of examples that I realized like I can't come up with these by myself. So we, with the help of our CDS and a bunch of other folks, created a website called marc.ncan.uidaho.edu where you can go and play pre-approved puzzles that have been submitted. And you can actually also create your own. There is an official competition that we've got going on. It goes through November 30th of this year. We're going to evaluate submissions based on how easy is it for other humans to solve them, how hard is it for AIs to solve them. So we're taking these puzzles and we're testing them against other kinds of AIs, as well as creativity. How does that get judged? That depends on the prize sponsors over there. So we have, and huge thanks to the library who have come up with some really great examples. So not only is there a $500 prize for the best student submission as judged by the library and a $500 best faculty submission or staff submission by a judge by the library, but also a 3D printed bragging rights for trophy for best submission by a senior leadership. So I'm trying to get Tori Lawrence and some other senior leadership to try to get some submissions in there. Some strategies that we've picked up for making these. One is to start with something like a simple sentence. The cat wants to play with a toy it cannot see, and then trying to think abstractly how to make a world representation of that in these grid worlds. Another strategy is to take an existing ARC puzzle, and we have a bunch of these, and then writing down how to literally solve it. In fact, we have a bunch of these as well, but then trying to paraphrase that into some kind of figurative one, right? So take a literal description and turn it into a metaphorical one. A third strategy that I've seen students use is to look in their field of study and like, here's a metaphor that we use all the time. How would I represent this abstractly in these grid worlds? And a fourth one is to create a kind of visual narrative in your field of study. So The next 3 days, from 12:30 until 3:30, we're actually going to have a tabling session here at the library from 12:30 until 3:30. You are invited to join. You are also encouraged to invite others to join who are interested in playing around with some MARC puzzles and trying to create them. I think Normie said we'll be over there somewhere. Yeah, so we'll have the next 3 days sort of tabling. So please come, make MARC contributions, and help us with the MARC project. So I'll take any questions if you have them. Thank you. Any questions? Yeah.
This goes way, way back. So you talk about AI and intelligence and the Turing test. So passing it doesn't meet the necessary condition, doesn't meet the sufficient condition. So are there conditions it meets, or are we just pursuing intelligence as like a vibe?
Yes, so long as what you mean by vibe, as in an empirically sort of like somewhat grounded vibe, right? Because what Turing thought was like, there's this funny phrase is like, asking whether a machine can think is about as interesting as asking whether a submarine can swim. He's like, that's not the kind of question we should be asking. He wants to think about this in some other kinds of ways, right? So as long as that other vibe is a kind of empirical vibe, yes. But if in terms of like a philosophical one, he didn't think we could make much progress in that.
Without a guiding goal, is it anything besides a vibe? Or are we just making metrics up to fit whatever we're vibing with?
Yes, as long as you don't think, or I don't think making up is a bad thing. I think this is how we do for each other all the time, right? We make up games and we do all these sorts of things to sort of like test and play around with each other. But yeah. Does that answer your question? Yeah. I mean, I think we're making a lot of stuff up, but we shouldn't feel bad about that. I think that's kind of what we do. Money's made up. We made it, right? There's no like metaphysical facts about money. We made it up. And it's a very good thing that we've made it up because it is convenient for lots of other things and tracking sorts of things, right? But money's made up.
I mean, so is the necessary and sufficient condition. I mean, technically, we can decompose everything into being made up.
Yeah, fair enough. I mean, I don't think that's quite right. I mean, there's some things that I think are harder to, that are less conventionalized. But I do think that like what we've learned a lot more about intelligence than we thought. We, I think, realize now that there are certain kinds of capacities that are not just purely linguistic capacities. And I mean, we've passed the Turing test, right? Like this is now basically been regarded as like we've moved well beyond that now. The competencies that large language models have of anything that you want, if you want to do anything to make them seem more human-like, it's to actually kind of like dumb them down, right? To purposely make grammatical mistakes, to talk in a certain kind of way, right? Because now when a student submits something, I'm like, oh, that was definitely written by an AI because I've read enough AI-style things, right? So there, it's sort of like we're trying to emphasize something about the performance of them. I feel like
You did great. You did great. Thank you.
Yeah, Wayne.
Obviously, very much.
This is obviously just an opinion. Do you think AI gets to the point where it understands how to solve these puzzles?
Yeah. I don't know how far away it's going to be, but once they do, I'm really interested in figuring out how. I think one of the sort of things that's really interesting with a lot of these models is even while they're able to pass the benchmarks, we don't quite understand how it is that they're doing that. And I think there's a secondary question of like, what is it exactly that they're doing to be able to solve these? And then using that as potentially as a point of comparison between like how exactly do humans do it? Are they similar? Are they different? Is there some kind of general principle that we can access here about how to solve these sorts of things? So I think there's lots of interesting downstream questions even once they solve these kinds of tasks.
You think that there'll come a point at which humans collectively can't come up with a new benchmark that is not easily solvable by AI?
Eventually, yeah. Maybe the harder question is like, in how many years? I think we're actually still a long, long way out for a few different reasons. One, we've only, I think, just started scratching the surface on these sort of like narrative sort of qualities that I think are underrepresented in a lot of the other kinds of benchmarks. And if we just look at some of those other benchmarks, there's a way in which they have these sort of like symbolic closures that I think things like narratives and metaphors don't have quite the same kind of features. And that's just like on the linguistic visual sense, right? I think once we get past that, we'll move into like dynamic environments. I know that the ARC Prize, they're already working on ARC 3, which is going to be like these little games where an agent has to like learn certain properties on the fly to solve them, right? That's already a big issue. And I think once we move to like even simulated virtual environments, we'll just try to get them to play soccer and baseball. There's like this really fun competition called World Robo Cup, which is to try to get robots to play soccer again at the human level capability by 2050. It's hysterical to watch this attempt. And even if they get that good, I think we'll just invent new actual sports called dishwashing championship, where they have to load dishwashers. I think we're a long ways out in terms of like exhausting our own creativity of what they won't be able to be good at. Judged by mothers. Okay. Oh, yeah.
This is very much not, this is going down a tangent. How do you think as AI continues to sort of invade our society, how do you see teaching change?
Yeah. I've at least deployed one of two strategies. One is the online version is hopeless. I just can't possibly police whether a student is just using a bot, even now, right? So I have alternative strategies for being like, I hope that some good faith efforts, and I try to make the exercises online somewhat interesting, and I actually have my students interact with AI agents who have like different beliefs, right? As opposed to a discussion board. And then the other version is good old school, no screens. So I teach critical thinking where you bring pen and paper, you're going to learn how to write notes for yourself. We do everything old school. You got to use your brain. And for 50 minutes, you get a break from no tech. So I've moved to those two extremes. I think it's a huge challenge to try to navigate the in-between spaces, and I haven't found anything that's quite as compelling. And no matter what, you should develop your own intelligence, even if there's another more intelligent thing out there, right? Just because Kasparov is really good at chess doesn't mean I shouldn't try to improve my chess pieces, right? There's always going to be someone better out there than you for that. Yeah. So I think, maybe to answer your question more directly, I think we're in a position where we want to significantly reevaluate what the value of an education is. And I think the argument that we have been using for quite a while now, that it's a good economic bet because you'll get a better job, I think is losing its foothold. And some of the original motivations for a good education, which is to be a better person and to excel as a human and be a good citizen, I think we'll be hopefully revisiting those reasons for getting an education. That's a kind of cool end note. So I'd like to maybe just end it there.